In this video, I want to discuss the impact of the character of the input on how well a method runs. So in the past, basically we've been making this assumption that the only thing I really care about in terms of input is the size of it. So any array of size 10, it'll look the same. And maybe you can get that, right, from the growth function. The growth functions are written something like f of n. There's only one thing there, right? There's only an n there. So if I have, different arrays, they all have maybe different stuff inside. They all, if they're the same size, then, well, they all look the same to that growth function, right? That's what we've been assuming so far. Let me actually draw a little bit here. So let's say, for example, we have n equal 5. So if we were to go over here and say something like A, B, C, D, E, that's an array of size 5. I give it to a sorting program, right, it'll do its stuff. But I also have different inputs, right, of that same size. Maybe I just have the reverse order. E, D, C, B. And there's a little bit of an issue here, right, in that these things look different, but they're the same size. And up until now, we've made the assumption that, oh, they're the same size, so they're equivalent. And that just really isn't the best assumption to make. So let's say that we have this linear search program. So linear search is a program, right, that basically looks at the input pool of elements, and it tells you, is this element in that collection or not? Is it in that array or not? Well, if we think about maybe searching for something like A, right? A in the input, right? And the input can be the same size here, right? So I have here, right, two different inputs. Okay, say that they're size 5 here, right? I feed them both to this program as the pool, right? Our target may be something like A. If I run this program on that first input, say this is input 1, what happens is I finish immediately, right? So because the data is set up a certain way, because it's sorted, right, A, B, C, D, if I run linear search on that and I'm looking for A, it's basically done, right? The first loop, right, looks at the first element matches and it returns true. Done, right? Really, really easy, right? Very little computation to do. So maybe if we were saying here, we're doing some analysis on this and we want to do analysis, the right way and choose a good cost metric, maybe our cost metric could be something like the equality, right? Equalities are nice because there's something, well, here it's nice because it happens inside the loop, right? It's something that happens very frequently, and it's very kind of core to the idea of the algorithm, right? Checking to see whether something is in a collection. So it would be reasonable to count up the number of times that occurs. But if I have my input of size 5 that goes from A to E, what would happen is this is only going to cause us to do one comparison, which is, it's okay, it's nice. But what happens if I put the second input in there? If I put the second input in there, in the reverse order, E, D, C, B, A, well, I'm going to need more than one comparison. In fact, I need 5 comparisons, because my linear search is going to go and look at each of those elements in turn until it gets to the very end. And so now I have this over here. This goes to 5. So what is our result? Our result, right, conceptually, right, our result here is a linear search is dependent on its input size. A linear search is dependent on how its input looks. So if it looks one way, it'll work quickly. If it works another way, it'll not work quickly. But because it has that kind of character, it's no longer fair game for us to write an exact growth function, right? I can't have a function that I can't have this, right? This is bad, right? F of 5 equal 1, f of 5 equal 5. That's like absolutely horrible. Don't ever do that. That should make you very sad if you've paid attention in math classes. That's not a function. And again, right, the issue here, right, is that how the function works depends on how the input data looks. Generally what this implies is that we do not have a growth function, right? It may not be possible actually to write a growth function for a particular program if there's this dependency. And so unfortunately this happens it's uncommon, right? So you'll see it, although it's not super common. So there's a lot of things that a growth function does not exist for. And in that case, what we're left with is using something that's an approximation, something like a bound. So in this case, right, if I were to summarize my analysis here, I would say that my f of n, I'll say that does not exist. I'll actually come back to that because there's a way we can force it to work. But the only thing we could really say is that this is maybe something like big O of n. Right, so this particular function here even though I can't tell exactly how many times I need to make that comparison, what I can see is, oh, that comparison happens within a for loop. That for loop happens up to n times. Well, that's kind of like a worst case, right? N comparisons. So, oh, hey, that's big O, right? That's worst case there. So this whole thing could be big O of n. So this would be a fair analysis. That would be good to go. But again, the issue is that our straight up growth function simply does not exist because the function basically isn't predictable enough, right? The amount of work it has to do isn't predictable from the input size alone, right? From the size of that array. And that is an issue. One thing we could do, maybe we want to somehow fix this, is say, okay, I can make an additional assumption about how my input looks. And so I can say, okay, I can assume, for example, that it's already sorted. If it's already sorted, then hey, my growth function is basically going to be f of n equal 1 or f of n equals 0, depending on whether it's there or it's not there. If it's sort of reverse order, right, I can make the assumption that it's going to be f of n equal n or something like that. Point is, if I make additional assumptions about my input, I can maybe then use those constraints to actually write a growth function for that. But I need additional assumptions. The size of the input is not enough. One very common thing to do here is basically to assume that our input is randomly shuffled. If our input is randomly shuffled, we can actually say the following: f of n equal 1/2 n. And what that means is it means that we say, okay, on average, right, I will have seen my input by the time I get through half of the data, right? That's that 1/2 doing there, right? We have to explore 1/2 of those n elements before we're likely to see something. And once we see it, well, hey, we can return true. So this falls into something that's called amortized analysis, and we're not going to talk a lot about that in this class. The only time we'll use it is the only time we'll use the idea is basically to say, okay, sometimes when you have a pool of elements, we'll just randomly assume that we'll assume that they're randomly ordered, right? Because then we can don't have to worry about these edge cases of, oh, it's done really quickly or it's done really slowly. If it's just all random, then we know there's for sure going to be work to do. So just kind of keep that in the back of your head, right? That's another way to approach this, but we need additional assumptions. So to answer that question there on the bottom, right, hopefully you got it, right? No, it's not possible to write a growth function for that. It's also not possible to write a growth function for something like the return. The return is something that basically I have to know, is the element in the collection or not, right? If I do, then the growth function for that is 1, otherwise it's 0. And the opposite holds for the return false over here. Okay, so having said that, having worked out analysis, let's actually look at sorting algorithms for a second, because sorting algorithms have basically the same issue of input dependence. So hopefully in your previous courses like SER200 or CSE205 or CSD200 or many of the other classes that serve as prereqs for this, you've seen the algorithms for insertion sort and selection sort. So those are two algorithms that basically we give them some pool of elements, and at the end of the day they produce for us those basically that same data, but now in a sorted order. So maybe it's ascending, maybe it's descending, it doesn't really matter. The point is it's ordered according to some rule, right? Less than or greater than. Okay, so think about those sorting algorithms for a second, right? Insertion sort, right, is about this idea of taking an element and basically shifting it into the place it belongs, whereas selection sort is about reaching into your collection of things to sort, taking out the smallest and putting it at the front, and then repeating it. So it's basically adjusting one element at a time, versus insertion sort is about shifting over one element, which may kind of involve touching many other things along the way, and then getting it into its right position. So those two different algorithms. And these algorithms are basically an example, right, of things that solve the same problem, but one of them has a little bit of a different behavior depending on how the input looks. Now, if I have something like a selection sort, I can run it on any input of a particular size, and it'll all act the same. So if I have an input array of size 10, right, it just doesn't matter what is in there. So it could be sorted already, it could be completely unsorted, it could be in reverse order. No matter how it looks, selection sort will take the same amount of time. It'll always apply the same algorithmic kind of shuffling or deshuffling to generate its output. So that's what I'm trying to basically indicate here in this graph. This graph on the right hand side, what I have here is this axis over here is supposed to be number of operations. And you notice here this is basically constant. So what I'm saying is, oh hey, no matter what you give it, the same number of operations will be executed. And then over here on this axis, which is a little bit tricky, this stuff over here, these are basically different inputs. So maybe this could go from ordered inputs over here to unordered. And even if something is really ordered, right, it still takes the same amount of time as something that's really unordered, right? That how the input looks just doesn't impact how selection sort acts. Okay, so that's pretty nice. That's actually one of the advantages of selection sort. It's very kind of reliable in terms of how much memory it uses or how much computation it uses. On the flip side, insertion sort, which also solves the same problem, does not have kind of that level of reliability. It's actually going to vary with what the input looks like. So worst case for insertion sort is look at something that's completely unordered. So if something's unordered, insertion sort will look something like a couple of nested loops. It'll be something that's like big O of n squared. It's this line over here. So this is unordered. So that's okay, right? If we were to look at something like a selection sort is also O of n, so maybe there the behaviors are comparable. Now what happens though is that in insertion sort, if I already have an input that's sorted, it acts completely different. It doesn't actually have nested loops anymore. It just has one loop. One loop that goes and looks at every element and checks to see where that element is in its proper place. For an unordered case, right, insertion sort will have two loops because it uses the inner loop to push the unordered elements into their proper position. But here, right, if we say, oh, hey, things are ordered, the inner loop basically never needs to run because that element doesn't need to be shifted into its proper position. So we're good to go. So it turns out that if I have things that look sorted, insertion sort acts much, much more like a linear time algorithm. So it looks like O of n because somehow it turns from the sorting problem into the verification problem, right? Check to see whether this array is already sorted or not. That's what insertion sort is effectively doing on an input that's already sorted. So this is another example of input dependence. A lot of times, right, when I'm writing code that has this dependency, and it's basically something for us to, well, we do need to worry about it. Usually what happens is, well, what we hope it happens is something like insertion sort, where we can find a good upper bound like O of n squared for it, and then in the back of our heads we think to ourselves, oh, cool, you know what? That algorithm, there are cases where it'll do better than that. It'll look more like O of n, right? Or have a growth function that looks like n. That's nice, kind of knowing in your back of your head, right? Not just that it'll only take at most n squared time, but that there is a good chance it'll take a lot less. So that's a very nice thing to know. Although if we're writing this down, we do need to be paying attention, right, to that worst case, because worst case generally are what gets us in trouble. All right, so that should give you guys a general feel for how basically methods may depend on their input. Try to keep in mind, right, that there's this dependency, and when the dependency exists, growth functions typically don't exist, but we still have a chance of doing some sort of big O style analysis instead.